Welcome. This video is going to go over the solutions to the Chapter 2 test. And again, try and concentrate on the difference between Paper 1 multiple choice and Paper 2 the free response and how to maximize your points on each of these exams. So question number 1 says, which statements about isotopes of chlorine 3517 and 3717 are correct? And your choices are they have the same chemical properties, they have the same atomic number, or they have the same physical properties. So what you should realize is that the 17 is the atomic number, and they're both chlorine, so that is true. Isotopes have to have the same atomic number, be the same element. So really the question is, do they have the same chemical or the same physical properties, or both? Well, the same chemical properties are true because we can't tell when we have a mixture of isotopes. But it's the physical properties that change because we can see right here the mass is greater, which makes the density greater, and affects some other weight-dependent characteristics like boiling point and melting point. So A, 1 and 2 would be our best choice. And then scrolling down to number 2, which is correct for the following regions of the electromagnetic spectrum. And they're comparing ultraviolet and infrared. And the way I remember this is Roy G. Biv is the visible part we see, with violet being one end and red being the other. So UV is just beyond the violet, and infrared is just beyond the red that we can see. So these are the two electromagnetic waves just beyond our sight. And to remember which one is the high energy, high frequency versus which one is the low energy, longer wavelength. I just remember that UV is in the sunlight, and that's the one that damages us. So it's going to be high energy, which corresponds to a high frequency or a short wavelength. And infrared then is going to be lower energy and lower frequency. So A is the one that fits this descriptor. Number 3 says, consider the relative abundance of the isotopes of the element X. So you have 80% 24, 10% 25, and 10% 26. So the relative atomic mass then is going to be your 80% times 24, 10% times 25, and 10% times 26 added up. So A and B aren't possible. You're doing a weighted average, and you can't get exactly 24 and 25 unless you had 100% of those isotopes. So then the question is the average going to be closer to 24 and 25 or 25 and 26? And with an 80% abundance, it's definitely going to be closer to 24, in the 24 to 25 range. Number 4, which statement about the species 63 Cu2 plus and 65 Cu plus is correct? So in each case, you have copper. So in each case, we're talking about an atom with 29 protons. But they each have a different number of neutrons. This one has more neutrons. And they have a different number of electrons because the 2 plus indicates it's lost 2 electrons. This one only has 27 electrons, whereas this one has 28 electrons, and a neutral atom would have all 29. So the electrons and neutrons are different for both of these. And because the electrons are different, electron arrangement is going to be different. So the only thing that's true about these two isotopes is that they have the same number of protons. Number 8 asks, what is the relative atomic mass of an element with the following mass spectra? So you see we've got isotope 23, isotope 28, definitely more of the 23. So our choices all range between 23 and 28. It should definitely be closest to 24, and you could actually punch these numbers in, but 0.8 times 23 is going to put you very close to 24. Number 9 wants to know how many protons, neutrons, and electrons are present in each atom of 31 phosphorus. So 31 is your mass number, so you have to look up your atomic number for phosphorus, which is 15. Since there's no charge here, that means I have 15 protons and 15 electrons, which leaves me with just B and C as possibilities. And then the 31 minus 15 means it should also have 16 neutrons, leaving B as the best answer. Number 10 is similar. How many electrons does the ion 3115 phosphorus with a -3 charge contain? Well, 15 is the number that reveals the electrons in a neutral phosphorus atom. So if it's picked up a -3 charge, then we can assume there are 18 electrons in that species. Number 11, which describes the visible emission spectrum of hydrogen. Converging would be the key here. You should know it's not regularly spaced because the book made a big deal of the converging lines. And it's a series of lines converging at longer wavelength, series of lines converging at lower energy, or a series of lines converging at higher frequency. And you're expected to remember that when you're at N1, the biggest step is to N2, and then it gets closer to N3, and even closer to N4. This is your higher frequency. So D, the lines converge at higher frequency for hydrogen or any element spectra. So those are the 11 paper 1 questions, and hopefully going through those, you see how you should have been able to eliminate choices and honed in on the correct choice within 2 minutes on each question and without using a calculator. Number 12, looking at the free response, 12A was, or 12 was pretty straightforward, very similar to questions that were in your problem sets. Explain why the relative atomic mass of argon is greater than the relative atomic mass of potassium, even though the atomic number of potassium is greater. So what they're telling you is that K has more protons than argon has, and yet argon has the greater mass. Well, the only other thing that makes up mass is neutrons. So you could have simply said argon has more isotopes with more neutrons, or argon has more neutrons on our average, or you could have used the word isotope, that argon has more heavy isotopes than potassium. But that's what they're getting at, is that because argon has more protons, the only thing that can be making it heavier is neutrons. Part B, deduce the number. A lot of people ask what deduce means. It just means, reason out or figure out the number of protons and electrons in the K+. So again, if you look up potassium, you see it's element number 19. So that means it has 19 protons. That's solid. That's not going to change. If it's picked up a plus one charge, it has to have given up an electron to do that, leaving it 18 electrons. Part C of number 12 asks you to deduce the electron arrangement for the K+. The electron arrangement, because they don't ask specifically for configuration here, a noble gas or otherwise, you could have just used the IB one. 288 accounts for all 18 electrons when it's become a K+, because it would be similar to argon, or you could have written out the full configuration. Either one was just fine. Number 13 was a little bit bizarre. They asked for the emission spectra of hydrogen, outline how the spectrum is related to energy levels. So that's what they really wanted you to key on, is 3 different things connected to the energy levels. So the 3 marks I didn't think were very clearly outlined as to what they were looking for, but there were 4 things that they would have given you a mark for. To mention that the emission spectrum is a series of lines, or you could have said discontinuous spectra or line spectra would have been fine terms to use. And they wanted to know that the energy is released when you move from higher to lower levels of energy. And you could have mentioned that the lines converge at higher frequency or shorter wavelengths. Or you could have described the 3 different spectra, that going from a higher level down to energy level 1 produces the UV, from a higher level to level 2 produces the visible, and from the higher level to level 3 produces the infrared. Those were the things they were looking for on number 13. So number 14, this wasn't really real different from the ones you had in your problem set, so I was surprised how many people had trouble with it. You see I crossed out my work up there because it was a little bit hard to follow, so I've redone it here, and some of you like to go ahead and convert your percents to decimals, so you'd have 0.031 in here and 0.969. That's fine. But what I like to do is set it up as the percents and divide by 100, because then when I multiply both sides by 100 and distribute through, I have 2809 equals 93. Plus then I take the 29, if you can't read that, 29 times the 96.9 is 2810.1 plus a negative 29x plus the 28x. And the idea here is just like when we do it with just 2 isotopes, that if I know one of the isotopes is 3.1%, then as I showed up here, the other 2 isotopes have to add up to 96.9. So I can think of those percentages or abundances as x and y, and I could solve for y knowing that x plus y has to add up to that missing 96.9. So you're just doing substitution. And so then when I simplify here, I end up with negative 94.1 on the other side. So multiply both sides by negative 1. And X then, which is isotope 28, and that's the one we're interested in, has to be equal to 94.1%, which was my answer up here as well. So number 15, virtually the same question for part A. Calculate the percentage of each isotope. I've got rubidium 85 and 87. Together I know they have to add up to 100. So if I've got X percent of 85, then I have 1 minus X, or 100% minus X of the other. And then when I solve for it, I came up with 23.5% and 76.5% respectively of each one. The second question, B wants to know, it says a percentage of each isotope can be checked experimentally using a mass spectrometer. It's vaporized, ionized, accelerated. Outline how the use of a magnetic field and a detector in the mass spectrometer enables the percentages to be determined. So what they wanted you to know is that the magnetic field does the deflecting. The light ions get deflected more or bend around the curve better. The heavy ones don't bend as well or deflect as much. And then the detector converts all the hits of those isotopes banging into the wall, converts it into an electric signal, and that's where they come up with the percentages. They look at how many isotopes are hitting where on the machine and convert that into the percent abundance. And then C was really pretty straightforward. It's not an ion, it's just an isotope. 87 rubidium, all they want is electrons and neutrons, so you look up the mass number, or the atomic number for rubidium, and see it's 37, which means it has 37 protons, 37 electrons, since it's not an ion. Subtract to get your 50 neutrons. And that finishes up paper 2 for this exam.